Hey everyone, and welcome to another video. Today we're going to be talking about radicals versus fraction exponents. And of course, you can see in the video up here it says rational exponents, but a rational number is just a number that can be written as a fraction. So really what we're talking about is what does it mean to have a fraction exponent? So let's ask ourselves, what would it mean to have x to the 1/2? Well, I don't know, but let's multiply it by another x to the 1/2. Now, according to what you know about exponent properties, when you multiply two things that have the same bases, you add the powers. So this is x to the 2/2, or in other words, x to the first. But you'll notice we've multiplied the same thing twice, and we got x. What do you call it when you multiply a number by itself and get a particular other number? You call it the square root. So the square root of x multiplied by itself is also going to equal regular old x to the first. Of course, let's remember that x is the same thing as x to the first, and 1 is the same thing as x to the 0, unless x is 0. So what we're concluding then is that square root of x is the same thing as x to the 1/2. And using a similar logic, we can argue then that cube root is x to the 1/3. Fourth root is x to the 1/4. And if I just pick any numbered root, it is equal to x to the 1/n. Okay, I'm going to leave that on the screen for just a second and think about, well, what does it mean then if I have x to the 2/3? Well, again, we're going to come back to exponent properties. And in particular, we're going to use the power to a power rule. And we're going to say this either means x to the 1/3 to the second, or it's equal to x to the second to the 1/3. You can write it either way. Neither one's right or wrong. I'm going to use the top one though. So I'm going to say that this then, if it's x to the 1/3, we just agreed over here that x to the 1/3 is the cube root. So this is the cube root of x squared. And depending on which way you wrote this, 1/3 to the second or second to the 1/3, that'll determine whether this squared is inside or outside of the radical. So what we conclude from that is that they're actually interchangeable, whether we put the square inside or outside. So when we deal with our fractional powers, we're really just doing a combination of regular exponent for the numerator and root for the denominator. So fraction exponents. The numerator is the normal power, and the denominator is the I'll just write the radical, but it's like the number of times radical, like the what root, right? Like so if it's 3, it's cube root, if it's 4, it's fourth root, etc. So this is what we need to remember when talking about our fractional exponents. And so when we look at this screen in front of us, we can see very clearly then that these questions are going to be pretty easy to answer. 7 to the 1/2 means square root, so it's square root of 7. 2 to the 5/3, well, this is 2 to the 5th, 2 to the 1/3. 2 to the 5th is 32, and to the 1/3 is cube root of 32. 6 to the 3/2, 6 to the 3rd, square root of, which is square root of 216. Now, there are arguments to be made that you could reduce some of these. You could say, for instance, that this is 6 root 6. We could have said this is 2 cube root of 4, but I get the impression that this this page doesn't want us to do the simplification. And furthermore, I think that's something we're actually going to talk about on one of the later sheets. So for right now, we're just going to do the conversion and leave it at that. So 4 to the 4/3 is going to be 4 to the 4th, and the 1/3 power means do the cube root. We do want to simplify the 4 to the 4th though, so that's, I believe, 256. 16 times 16, yeah. Okay, 7 to the fourth cube root of, I don't have a calculator handy, so I'm just going to leave that one alone and you can tell me what that's equal to. It's like 2403 or something silly like that. And 2 to the 1/6, well, we don't have to raise it to a power. We can just straight up say sixth root of 2. Easy enough. Now, for this page, we're going the other way. We're saying square root of 10 cubed is 10 to the 1/2 to the third, and now power to a power rule, 10 to the 3/2. Obviously, with all this, you have to be very comfortable with your exponent properties. If you're not comfortable with your exponent properties, that might be something you'll need to practice a little bit. But all of these rules, all of these questions are going to be related to if you know your exponent properties well, because they translate very easily into making these questions very direct. So cube root, 2 to the 1/3. Didn't have to do anything more fancy than that. That's a 3. This is, well, that's right there. So obviously that's 2 to the 1/6. I love when questions are generated on a sheet like this and basically the same one is used multiple times or something very similar. And you can just kind of compare notes. So, all right, 5 to the 1/4 to the 5th is 5 to the 5/4. And finally, this is 10 to the 1/6. Okay. Now, for these lower questions, we're going to have to be a little more careful for two reasons. First of all, there's more than just a number inside of the parentheses. And number two, some of them have negative exponents. So, two things to note. If parentheses are to a power, the whole thing is to the power, meaning each of the individual factors gets raised to that power. The other thing to note is that negative exponent means flip to the other side of a fraction. Normally we think of it as or 1 over whatever it would have been otherwise. But I write it as flip to the other side of a fraction because if it's already in the denominator, you're going to flip it up to the numerator, which I don't think we're going to see in any of these questions, but I want to be thorough here and talk about all the possibilities. So, okay, 5x to the negative 5/4. I'm going to break this one down. I'm going to say it's 5x, and then we're going to say parentheses to the 5th bracket to the 1/4 brace to the negative first. Now, do I have to write it like this? No, but I want to make it very clear what's happening so we can address this one step at a time. So let's talk about first the parentheses. 5x to the 5th is going to be, well, 5 to the 5th, 25, 125, 6 to 3125, x to the 5th. And then consequently, we need to do the 1/4 power of that. So that's to the 4th root of, and then we have negative exponent, which means it's now 1 over. So this whole thing right here, whoops, don't bring the 1 with me, but anyway, there's my answer. And can I get that 1 to go, please? Can you let me move it? Oh, come on. Zoom, zoom, be nice. All right, we'll erase it and rewrite it. But that's how that basically plays out, is break it apart step by step by step. So now 5x to the negative 1/2 is 5x to the 1/2 to the negative first. And we would have had 3 layers had there been a numerator that wasn't 1. All right, so 5x to the 1/2 is a way of saying square root of 5x, and it's negative exponent, so now it's 1 over. And there's your answer, 1 over the square root of 5x. That's not generally the way we like to leave responses like this. So if you feel that you need to, say, rationalize the denominator and raise root 5x over 5x, that's a very valid answer too. And your teacher may prefer that. But honestly, that would require doing a lot more work on this other question over here. So I'm going to leave that one under the rug for right now. All right, 15, 10n to the 3/2. So 10n to the third to the 1/2. And again, as I said before, we could have flipped the order of the to the third and to the 1/2. But because we're going to be doing the 10 to the third as well, I think we want to do the numerator first. So 10 to the third is 1,000. N to the third is, well, n to the third. And then to the 1/2 power means we're doing the square root of all of that. And finally, a to the 6/5, this is very direct. We have a to the 6 to the 1/5 power. All right, so hopefully that should be completely clear. If it isn't, maybe pause and rewatch it, but I think we've addressed everything that we need to know about radical and fraction exponents here. So I'm going to scroll this down now. We're going to see, oh my goodness, there's a whole boatload more questions. What in the world do they want us to do here? Well, 6v to the 1.5. Let's think about 1.5. That's a fancy way of saying 3/2, right? 6v to the 3/2, parentheses. All of this in parentheses. It has to apply to the 6 and the v. All right, well, that's 6v to the third, and then to the 1/2. So that is equal to, hold on, I'm going to move this over. Shloop. All right, so 6 to the third is 216, v to the third, and we need the square root. M to the negative 1/2, same idea as what we had before. I'm just shortcutting and doing it real fast. Now we go the other way. Fourth root of m to the third. Well, this is m to the 1/4 to the third, which in turn, using our properties, is m to the 3/4. Nothing has changed. Okay. Cube root of 6x to the 4th. Oh, are they just going to leave it like that? I mean, they can, I guess. So this is 6x, and then it's raised to the 4th and raised to the 1/3 power, so it's raised to the 4/3 power. V to the 1/4. That one's nice and easy. 6p to the 1/2, also very easy. Don't have to think too hard about these. All right, cube root, that's a 1/3 power, and that's a to the 4th power. That'll be 3a to the 4/3. If you're not comfortable doing it in one step, and I'm not assuming you will be, then break it down the way I did number 19. And number 24, we got to break it down, and we got to remember it's in the bottom of an exponent. So we've got 3k to the 1/2 to the 5th, and then because it's on the bottom, it's to the negative 1st. Or you could have just said it's to the negative 5th. Yes, that is also valid. But if we put all that together, it's 3k to the negative 5/2. So multiple routes to negotiating the order of how we get there. But if you see something else that's equivalent and gets you there, yes, it's probably also equally valid. All right, 9 to the 1/2. That's the square root of 9. Square root of 9 is better known as 3. 343 to the negative 4/3. All right, so we've got cube root of 343 to the negative 4th. And the cube root of 343, I'm pretty sure, is 7. So we've got 1 over 7 to the 4th, which again comes back to, I didn't bother figuring out what 7 to the 4th is. I think it's like 2301, 2401, 2401, I think it is. Because it's 2100 plus 280 plus 21. Yeah, okay. This one looks scary, but really just count the zeros and you'll realize that this is just straight 10. Because this number here is 10 to the 6th to the 1/6, which obviously is just 10 to the 1st. All right, 36 to the 3/2. Whenever you get these fabricated book questions, I always recommend you do the root before you do the power. Because if you do 36 to the 3rd, you're going to get an astronomical number that you then have to square root. Whereas you don't deal with that if you do the 1/2 power first. We're going to do 36 to the 1/2, and then we're going to cube it. So square root of 36 is 6. 6 to the 3rd is 216. X to the 6th to the 1/2, just power to a power rule. We'll treat that as x cubed. 9n4 to the 1/2. So it's 9 to the 1/2, n to the 4th to the 1/2, which is n squared. All right, and this is the question we had right over here. So that's just a 3, 3n squared. 64, n to the 12th, negative 1 to the 6th. All right. So that sounds daunting, but 64 is a power of 2. What power is it? Well, let's count on our hands. 2, 4, 8, 16, 32, 64. 1, 2, 3, 4, 5, 6. Oh, it's 2 to the 6th. So we have 2 to the 6th times n to the 12th to the negative 1/6. So if we were to simplify that, that's 2 to the negative first, n to the negative second, or in other words, it's 1 over 2n squared. Did I do that too quick? Am I too slick with that one? Well, we're getting another one right here. Let's pretend it's to the negative 1/2. All that does is put in the denominator. So 81 m to the 6th negative 1/2. Well, we're going to say that 81, we have to do a 1/2 power. So let's remember that this is a square root. So I'm going to write this as 9 squared m to the 6th to the negative 1/2. If we had chosen to, we could have also written this as 3 to the 4th. So if it had been a like 1/4 power, I would have gone with that version. All right, and now we apply our power to a power 9 to the 9 to the second to the negative 1/2 is 9 to the negative first. M to the 6th to the negative 1/2 is m to the negative third. So this is 1 over 9m to the third. And I feel like maybe I'm a little slick with how I'm doing this. If you don't like that, feel free to send me some comments and I'll try to come up with a better explanation. But I'm going to keep this moving forward because we've got a few pages to look at here. So we're going to zip into page number 3 of 4. And now we get to talk about the fun stuff, which is taking stuff out of our sock drawer. And you're going, what? Sock drawer? Who said anything about a sock drawer? Well, I'm saying stuff out of a sock drawer. I'm saying that this right here, that's a sock drawer. And you're looking at me and going, yeah, how is that a sock drawer? Well, let's suppose hypothetically that you have in your sock drawer, you have 12 black socks or blue socks, whatever letter you want, brown socks, anything starting with B, and you have uh, 10 white socks. And I ask, okay, how many times can you take socks out of your drawer? Well, the thing you have to remember is that in order to take socks out of your drawer, unless you're a particularly strange individual, you are going to take them out 2 at a time. So each time that you take socks out of your drawer, they got to come out as a pair. Well, how many times can you take the black socks out of the drawer if you have 12 socks? 2, 4, 6, 8, 10, 12. Sounds like 12 times. So you can take out 6 socks. 6 pairs of socks. And then with the white socks, we can do that 5 times. And now there is nothing left in the sock drawer, so we just don't write it. But if instead it had been B to the 11th, W to the 9th, because we lost a couple in the dryer. Okay, now let's think about this. How many times can we wear our black socks? Well, we take out 2, 4, 6, 8, 10, and we're left with 1 inside. So we're going to wear black socks 5 times, but unfortunately, we're going to have a sad, lonely black sock that's going to sit in the drawer and not get used until you do laundry. And the white socks, same deal. You're going to pull out 4 sets, but you're going to have 1 left inside. And if you're going to do something other than a square root, so let's say this was the cube root of b to the 11th, w to the 9th. Well, now the same is true, except now you are a mutant and you have 3 legs. And so therefore you need 3 socks at a time. So you're going to pull your socks out 3 at a time, mutant girl, and you're going to say, all right, so I'm going to pull out a triple of socks, 3, and then another triple, 6, and then another triple, 9. I'm going to pull out 3 triples, and I'm going to be left with 2 inside. Likewise, we're going to pull out 3 triples of the w, and so it's b cubed, w cubed, cube root of b squared. And that's exactly how we want to write it when we are simplifying this. So that is the one thing that we want to consider when we are pulling stuff out and simplifying, such as these first 3 questions up here. With other questions, I want you to remember that you can multiply roots as long as you are only multiplying inside numbers or only multiplying outside numbers. You will see that in action soon enough. You can add roots, but only like you are collecting like terms. So you cannot add the inside numbers. Do not mess with the inside numbers. And we're going to see what I mean by that in a second as well. All right, so let's talk about number one. Number one is a daunting question because we get this root 192. So we got to break that up first of all. What is 192? Well, let's see. 192 is 2 times something. 2 times 96. 96 is 2 times 48. All right, that's a terrible 48. 48 is 6 times 8. 6 is 2 times 3. 8 is 2 times 2 times 2. Those are all prime at this point. 1, 2, 3, 4, 6. So it's 2 to the 6th times 3. All right, so our question up here is 7 root 2 to the 6th times 3 times m to the 9th times n squared. So we got a lot of different kinds of socks in our drawer here. Plus we got this 7 floating around outside. I don't know, that's our shoes or something. So what are we pulling out? Well, we've got 6 socks of the 2 variety. So we will take them out as 3 pairs. We've got a 3, a lonely 3. We got nothing to pair it with. Whatever it went with, we lost it. Some special sock, but the other one's gone. M to the 9th comes out as 4 pairs. We got a single n pair. And oh yeah, by the way, we got this 7 floating around. So how does that simplify? Well, 2 to the 3rd is 8. 8 times 7 is 56. So we've got 56, and yes, I'm bleeding into the next questions area. 56 m to the 4th n square root of 3m. And yeah, that whole freaking thing is the answer. That's gross, I'm sure. But that right there, that is the answer to number one. So I'll take that. I will put a box around it to highlight what's going on here. And yeah, you probably do need to do all that work. You might be able to not do this factorization tree here if you can recognize how to break down 192 quickly. But that was a big enough number that I didn't want to try to guess at what square root goes into 192. It's looking like the correct number would have been 64. It's 64 times 3. And square root of 64 is 8. But I wouldn't have known that ahead of time. I only know that now by seeing the 2 to the 3rd out here. Okay, so how about cube root of negative 135 x to the 6th y to the 13th? All right, 135. Let's think about 135. 135 ends in a 5, so it must be 5 times something. 5 times what? 27. Okay, and 27 is 3 to the 3rd. Well, all right, so we're doing the cube root of, I'm going to switch to the text tool here and go with a nice tiny font. All right, we've got negative 3 times 5 to the 3rd times x to the 6th times y to the 13th, and that's still bleeding into our next area, isn't it? Yeah, it kind of is. Well, poop. All right. I guess I'll just have to pick this all up and move it up here. Will you take the text box, please? Thank you. No, take the text box. Come on, Zoom. There we go. There we go. All right, now we got it all moved. Okay. So, yeah, gross, but oh, I wrote this wrong. I'm sorry. It's not 5 to the 3rd. It's negative 3 to the 3rd. Okay. So ignore the negative for a second. We got 3 to the 3rd. 3 to the 3rd is going to come out of our sock drawer. We are now mutants with 3 legs, so we need a triple coming out, and we've got it. We got a 5 that gets stuck inside. X to the 6th is x squared outside. Y to the 13th is 4 sets on the outside and 1 left on the inside. Now, what about this negative? If this was a square root, we would have to write like times I. But cube roots, think about it. What is like a negative number to the 3rd power? It's still odd. In fact, specifically, -1 to the third power is -1. So in fact, this negative can just come outside because it's an odd root. We would not do that with an even root. A square root, a fourth root, don't do that. But with a fourth root, or sorry, cube root, we can do that. All right, so there is our answer to number 2, taking up a lot less space than we took up for number 1. All right, number 3, we are running out of space here, so I am going to erase our method over here on the left, or on the right rather. I hope that you're comfortable with that because we will be revisiting it. But 1250, now 1250 is another gross number, so I'm going to break it down. 1250 is 10 times 125. This is 2 times 5, and 125 is 5 times 5 times 5. So it means we've got the fourth root of 2 times 5 to the fourth times a to the seventh times b to the 24th. All right, now we can start pulling stuff out of our sock drawer, except now we have become cats or dogs or horses or some other four-legged creature that wears socks on each of 4 paws or hooves or whatever. So unfortunately, one sock of the 2 variety is not going to come out. This is like 2 to the first, right? We can't pull this 2 out. So now we got 5 to the fourth. Well, that's enough for a set for all 4 of our paws. So we'll take a 5 out. A to the seventh, we can wear A socks once, but unfortunately, then we leave 3 of them behind, which is oh so close to being a second set, but not good enough. But we got lots of B socks. So we're going to take all these B socks out. We can wear the B socks 6 times. And there you have it. There is our answer. As weird as some of these are starting to look, that is the simplified answer. Now you can question whether this is actually simpler than the original, but that is, in fact, what the question is asking us to do. All right, now, for onward, we're doing something a little different. That's where I was talking about the multiplying and the adding roots. We're going to simplify 27. We're going to treat this as root 9 times root 3. And root 9 simplifies to a 3. 3 times -2. This is -6 root 3. All right, 18 is root 9 times root 2. Root 9 simplifies to a 3, so -3 root 2. And then 72 is root 36 times root 2. You could have also done 9 times 8, but then you can break it down further. So I'm going to go right to 36. And this is plus 6 root 2. Now, we can do that, and then we can start combining like terms. We can recognize that these are both root 2's. And so if you have 6 root 2, take away 3 root 2, that's going to leave you with 3 root 2. And the -6 root 3 does not combine. So the answer is -6 root 3 plus 3 root 2. Oh boy, more of these fourth root things. 405. What the heck is 405? 405 divided by 5 is 81. Okay. So that's 3 to the fourth times 5. Got it. So 2 fourth root of 81, fourth root of 5. Gotta love these. Minus 3 times fourth root of 16, because that's 2 to the fourth, times fourth root of 5. And then I'm going to bet good money this is, oh no, there's not a multiple of 5. What is 192 then? 192, we did 192. It's actually over here. Okay, so it's 2 to the sixth times 3. So minus cube root of 2 to the sixth times 3. And I don't know how that simplifies, but it's not a root 5. All right, so fourth root of 81 is 3. 2 times 3 is 6. So we have 6 fourth root of 5. Fourth root of 16 is 2. Minus 3 times 2, that is minus 6 square root of, or cube, fourth root of 5. Well, those are going to cancel. I find it surprising that that happened to work out that way, but okay. It's interesting. Certainly was not expecting it to work out that way. But then we have minus Cube root of 2 to the 6th time, or fourth root, I'm sorry, no, it says cube root. I'm sorry, this one was a cube root. All right, so we don't want to mix these together. The fourth roots and the cube roots, don't mix those either. But this cube root, so we'll pull out two pairs, or two triples, and we get 4 cube root of 3. And as I said before, the stuff over here is going to equal 0, so we ignore that, and therefore this is our answer. Yuck. All right. Well, that was kind of fun. Kinda. All right. So now, referring back to what I said up here, we can multiply the inside numbers and we can multiply the outside numbers when we're multiplying these irrational numbers. So let's do it. -3 times -6 is a positive 18, and root 6 times root 8 is a root 48. All right, can we simplify root 48? Well, yeah, it's 16 times 3. 18 root 16 root 3. Root 16 is 4. 4 times 18 is 72 root 3. So that one's a little more painless. All right, outside numbers. 5 times 2 is 10. Inside numbers, we've got -3 times -36 is -108. W squared, W cubed, this is W to the 5th. All right, and now 108. 108 is equal to, we need a triple, 27 times 4. And 27 is 3 to the 3rd. So 10 times -3 times W, cube root of 4W squared. And then the 10 and the -3 become -30. And yes, I did this second step here on the page very quickly. So I'm going to ask you to stop and think about, how did I get all that and how did I do it so quickly? But that's going to be my response to this particular question. All right, for number 8, we got to follow the distributive property. Distributing a root 15, we get 2 root 90 minus 7 root 75. Now, both of these break down, I think. 90 is 9 times 10, so 2 root 9 root 10, and 75 is 25 times 3. So root 9 is 3, so 2 times 3 is 6, root 10. Root 25, that's 5. 7 times 5 is 35, root 3. Oh, and then we get to go one step further with our distributing. Now we get to do FOIL. All right, so first, 3 root 3 times 4 root 3 is 3 times 3 is 12. Root 3 times root 3 is just plain old 3, or it's the square root of 9, which in turn is 3. So I'm going to just call that whole term 36, 12 times 3. Then we do outer. 3 root 3 times 5 is plus 15 root 3. Inner. -2 times 4 root 3 is minus 8 root 3. And then we do last. -2 times plus 5 is minus 10. What do we do from here? We collect like terms. 36 and -10 are loose numbers, so that's 26. 15 root 3, take away 8 root 3's, leaves behind 7 root 3's. Don't worry about the root 3, just pretend it's the letter x. 15x minus 8x is 7x. 15 root 3 minus 8 root 3 is 7 root 3. Same thing. All right, this one's a difference of squares, so I can cheat this one. It's 1 squared minus 7 root 2 squared. So that's 1 minus 49 times 2 minus 98. I believe that's going to be negative 97. I realize I did that really quickly, but if you do your FOIL, I think you should get the outer and inner terms canceling, and this will be your first and your last. 5 plus root 12 squared. Okay, so if you know your binomial square real well, you can work with that. Otherwise, we want to write out another 5 plus root 12 to visualize our FOIL with. So first is 25. The outer is 5 root 12. The inner is also 5 root 12. And then the last is root 12 times root 12, which is 12. When you multiply a square root by itself, you just get the number underneath because it's 12 to the 1/2 times 12 to the 1/2, which in turn is 12 to the first. Okay, so 25 plus 12 is 37. 5 root 12 plus 5 root 12 is 10 root 12. And now this one's going to be a little more fun to simplify, I can tell. All right, still, this is like multiplying, except now we're dividing. Dividing uses the same kind of rules. So I'm going to say I'm going to cancel the 20 with the 5 and get -4. And 315, what is 315 divided by 5? All right, so 31, that's 6. We got a 1 left, so 63. Okay. Square root of 63. And we should simplify the root 63 because that's 9 times 7. So it'll be -12 root 7. Alternatively, you could have written this as -20 over 5 times the square root of 315 over 5, or you could have simplified the root 315 and tried to cancel down from there. That would have also worked, but I think this is probably the most straightforward approach. All right, square root of 12 over 27. So square root of 12, 12 is 4 times 3, over the square root of 9 times 3. All right, so this is 2 root 3 over 3 root 3, which is 2/3. Alternatively, cancel ahead of time. We can cancel a 3 from top and bottom and get the square root of 4/9. And square root of 4/9 is very clearly going to be 2/3. So two different ways to approach that I think are equally valid. All right, so there is a set of answers and solutions for how to do this. You might have found a different way to work your way to the answers on these, or you might have just taken a little longer and done a few more steps to get there. I am trying to go a little quickly so that this video doesn't take an entire hour, but that should give us answers for this third page. And now we're going to scroll down to our final page. Fun times are here again. Ready, let's go. Rewrite in radical form. Okay, so this is basically just a big old review. To the 1/2 power means square root. Except it also says in the instructions, simplify if needed. Oh. Root 4 times root 7, which is 2 root 7. 2 to the 4/3. Well, that's 2 times 2 to the 1/3, because this is 4/3 is 1 and 1/3, so I'm just going to write this as 2 cube root of 2. That's not how the person who made this sheet was intending. They figured you would do 2 to the 4th is 2 to the 6th. I'm sorry, not 2 to the 16th, just 16, or write as 2 to the 4th cube root of, and then say, oh, well, sock drawer. I pull 3 out as a set, and I leave 1 behind, which would be another way of writing this. Similarly, x to the 5/4 is x to the 5/4 root. So it's going to be x 4th root of x. 256x to the 1/4. Well, 256 to the 1/4 is just, no, it's not 4. That's, wait, 4/16. Yeah, it's just 4. I recommend knowing your early powers, by the way. No, like 2 up to like the 8th or 9th power, no 3 to the 4th or 5th, no 4 to the 4th, no 5 to the 3rd. And then know your squares up to like 15, because they show up a lot in teacher generated questions. So just hot tip there. And x to the 1/4 is just x to the 1/4. All right, mn to the 7/2. So that's the square root of m to the 7th, n to the 7th. Because if we think about this as mn to the 7th to the 1/2, right? Which gives us this version, 7, 7, that's a 7. I promise it's a 7. And so if we were to simplify that, what do we pull out of our sock drawer? We pull 3 sets of M and 3 sets of N out. And we are left with a single M sock and a single N sock behind. All right, I'm just going to shortcut this one a little bit here. Oh, wait, but this is to the 4th power. All right, hold on. We got to be a little more cautious about this. -2 to the 4th, a to the 4th, collectively then to the 1/3 power. So -2 to the 4th is 16, which is regular old 2 to the 4th. We're actually going to lose this negative sign because we're raising it to an even power. And that's a weird subtlety that I had to stop and make sure we talked about. But otherwise, we can just treat it like it is written the way you expect it to be. So it's 2a cube root of 2a because we have one leftover sock of each type. All right, rewrite an exponential form. 10 to the 3rd to the 4th is 10 to the 3/4 power. 3ab to the 1/2. The quantity 3ab to the 1/2 power. Cube root of 2w to the 5th. Quantity of 2w to the 1/3 and to the 5th power means it is to the 5/3 power. 4th root of this stuff. So this isn't a power to power thing. This is just, can you simplify this? 18 does not simplify in a way that we can get a set of 4. We can get a set of 2. It is 9 times 2, but that doesn't matter because we've got 4 legs in this question, not 2 legs. So we need 4 socks. So 3 to the 2nd cannot come out of our sock drawer. But x to the 9th can. So this is x squared, 4th root of everything that gets left behind. All right, simplify each expression. 9 to the 1/2, 9 to the 5/2. So it's 9 to the 6/2, or 9 to the 3rd, which is 729. X to the 7/3 divided by x to the 2/3. We subtract powers and we get x to the 5/3. Simplest radical form. This is not radical form, this is exponential form. So we have to put it into a sock drawer, a cube root sock drawer. There are 5 of them. So 1 set comes out and 2 loose socks stay in. All right, 28 to the 3/5 to the 5/6. All right, power to a power rule. Remember, we multiply. 3/5 times 5/6, we get a lot of cross canceling going on, and it's 28 to the 1/2, which is the square root of 28, which is the square root of 4 times the square root of 7, which is 2 square root of 7. This is a 7, not a 2. There, 7. Oh god, it looks even worse now. -64th to the -1/3. All right, don't get confused with negative exponents. The negative here means this number is negative. The negative here means it's 1 over. So don't flip those around. Let's just rewrite this as -64 to the 1/3 to the -1st. All right, so cube root of -64, which is -4. Because we do -4 times -4 times -4, we get -64. So we're going to get a -4, but it's 1 over that. So it's -1/4. 45 to the, I think that says -3/2 and not just 3/2. It's a little tricky to tell with the way that this worksheet is written, but -3/2 times 45 to the 2nd, those powers, you're going to add them together using exponent properties and get 45 to the 1/2. All right, so that's square root of 45, which is square root of 9 times the square root of 5, which is 3 root 5. 2 times 48 over 3 to the -1/4. All right, so 2 times 48 over 3 is 16. Let's just do that. To the -1/4, so we got a 4th root, and we've got a 1 over. All right, what is the 4th root of 16? 2, 4, 8, 16. Hey, that works out. So it's 2 times 1/2, because this 2 is not in the bottom. This 2 was outside. Let me pick up this 2 here, and whoops, no, that would not be picking up the 2. Come on, pick up the 2. There, I've picked up the 2 and moved it there. So it's 2 times 1 over 2, which is just 1. All right, fourth root of p times the square root of p cubed. Okay, let's be very, very careful here. This is not going to use the rules that I had written up here before. We need to use our exponent property. So we're going to write this as p to the 1/4 times p to the 3/2. P to the 1/4 times p to the 3/2. So power to power, or not power to power. Two exponents multiplied means we add the powers. So I'm going to treat this like 6/4. So this is p to the 7/4. And if we try to rewrite that in radical form, we got 7 p-colored socks. 1 will come out and 3 will stay inside. And yes, p-colored socks would be completely gross, I know. All right, let's rewrite this before we start messing with it. This is 24 to the 4/3 divided by 24. Okay, this loose number 24, what's the exponent on it? Think about that for a second, because we're going to do some exponent properties. Let's remember that 24 is the same thing as 24 to the 1st. So when we do division here, that's like subtracting the powers. We have 24 to the 4/3 minus 3/3 is 1/3. Okay, so we're cube rooting. We need to take things out in triples. So we have the cube root of 8 times the cube root of 3, which is 2 cube root 3. Okay, m over 4th root of m. So m over m to the 1/4 is m to the 3/4, because this, we're going to treat this as m to the 1st up here, and then we're going to subtract. So m to the 4/4 minus m to the 1/4 is m to the 3/4. And we can't really dress that up, but we can write it in radical form because that's what the instructions call for. So it is the 4th root of m cubed. All right, 16 over 4th root of 16 cubed is 16 to the 3/4. So once again, we're going to subtract our powers, and we get 16 to the 1/4, or 4th root of 16, aka 2. All right, 4th root. This is just a sock drawer question. We've got 4 legs, so we can't pull any A's out. We can pull B's out. We can pull up to 12 of them out as 3 sets. So b to the 3rd, 4th root of, and then what's left behind is a pair of A's and a pair of B's. If only we had 2 legs, we could wear these socks. Unfortunately, we have 4. All right, and once again, we've got 4 legs. 36 is 6 squared, or 2 squared times 3 squared. That doesn't break down. We can't take anything out of the drawer with that. But w to the 6th, we do have a set of W's we can wear for a day. And then we have to do laundry because nothing else matches. And we wouldn't dare set foot in the real world with mismatched socks. Maybe you would, but in the world of math, we don't do that. That's just uncalled for. All right, so that should answer this last page, and that should provide us with all the answers. So I hope that was helpful. I hope that this helped clarify what some of these gross questions can sometimes do. I know I answered some of these quickly, but hopefully that'll address all of your needs. So thank you and have a good day.